Now let's talk about JVM architecture. JVM architecture or Java Virtual Machine has three specific components: class loader, runtime data area, and execution engine. This class loader is further divided into three components. Now, what is class loader? Class loader is the first main component in JVM architecture. It has the specific three phases: loading, linking, and initialization. Let's first look at the loading phase of the class loader component. When we write any Java program and save it with the .java extension, after compilation we get a .class file. It is already explained. Now, class loader is responsible for loading this .class file into the memory. Now, to explain this, let's consider the first component of the class loader. Remember one thing, class loader has three segments and the loading segment contains three parts: Bootstrap loader, application loader, and extension loader. The Bootstrap class loader is the one responsible for loading the .class file from rt.jar. From this rt.jar, the .class file is fetched and saved into the memory. And this process is done by Bootstrap Loader. Now, what do you mean by rt.jar? It is very important, which is also known as runtime jar. For an example, when you write a code system.out.println, do you care about from where this system class is coming? System class is coming from java.lang package. Then my next question is, do we need to include java.lang package every time whenever we write system.out.println? The answer is no. The system class under java.lang package is available in the rt.jar. So Bootstrap class loader loads the system class from rt.jar to the runtime memory. So let's visualize the application or the functionality of Bootstrap Loader. This system class is written somewhere where it is written inside this rt.jar, right? And this rt.jar will load this system class into the memory. So it is done by the Bootstrap Loader. So whenever we have a source file and when it is compiled, we will get a .class file, right? This .class file is loaded into the runtime memory with the help of application loader. So application loader does a very simple task of loading .class file to the main memory. And now the question is, what is the purpose of using extension class loader then? Extension class loader is responsible for loading additional class files, say from JRE or from lib or from ext folder. In a simple explanation, I can say, if you have a source code and if you need to connect this source code with some database, then you need ojdbc.jar class file. In this scenario, we add this third-party jar file into the extension class loader. An extension class loader makes the pre-compiled class file available to the JVM by loading files to the memory area. So extension class loader does what? This required JDBC, ODBC jar files for maintaining a connection with the source code and the database. This additional file is loaded into the memory with the help of extension class loader. So Bootstrap loading is the simplest task. It does what? It does a simple task of loading system class into the main memory. As a result, we don't have to include the lang package corresponding to the system class. Application loader loads the class file and the extension loader loads any additional file for special purpose like database connection or anything else from the JRE or .lib or .ext library to the memory. So loading part is over. Now we will move to the link part. The purpose of the link part is to verify the generated class file. Now verification means what? Once the class file is loaded to the memory, there is a verification phase, and this verification is done by linking phase, where the bytecode class file are verified if they are conforms to the standards or not. So this is your basic class loader and its component and their corresponding functionalities. Now we will talk about runtime data area. So this segment is the next or second main component of JVM. Just like a car that needs a road or a train that needs a track to run, similarly JVM needs a memory area to store the class files. This runtime memory area is comprises of many types of memories like method area, heap memory area, stack memory area, program counter register, native methods. However, we only discuss about stack memory area inside the runtime data area. So now let's concentrate on the second component, runtime data area, and its stack memory application. I am going to explain one of the component of the second main component of JVM known as runtime memory data area, which is known as stack memory. So I am explaining stack memory from runtime memory data area. Now what do you mean by stack? You can say stack is a data structure. Or you can say stack is a abstract data type. What is the meaning of abstract data type? Simply, what operation I can perform on a particular data structure, it is predefined. That kind of modeling is known as ADT. So in stack, we can perform two specific operations. Basically three, but two major operations, push and pop. Now what is push? Inserting item one by one is known as pushing. So when pushing is done, then stack is known as full. And then the next item is popping, means deleting item one by one starting from the top of the stack. Now when the stack is empty, the pop operation is done. Now you can think JVM contains stack. But as this diagram shows, this JVM comprises of an entire stack, but you have to visualize that the JVM is divided into three parts, and this stack is a part of the second component, runtime memory data area component. Now we have many types of stack inside the JVM. Some stack are known as operand stack. Some stack are known as local variable stack. So what is the purpose of this stack? Say you have a code. No need to understand this code. Just focus on a particular area. Here. Here we have a method where I am performing 20 plus 30. As we know, it is a source code, and after compilation the source code is converted to bytecode. Now there is a way how we can visualize a bytecode. Whenever I write this line in the command prompt java p minus c and the class name, then I will be able to see this bytecode. This bytecode is comprises of two operations, push and pop, or you can say there is another operation which is known as very basic operation in computer science, load and store. Now how they will work with respect to this method, I will explain. So this is your operand stack. We have a pointer here and we have a local variable stack. And what is the meaning of these lines? I will explain one by one. See the animations carefully. So first, bi push 20. The meaning of this is push the value 20 into the operand stack. Then stack pointer is incremented by 1. After that, the program counter comes to the second line. Now why we have 2 after 0? Because here I am considering the size of the integer is of 2 byte. That's why after 0 we are getting 2. Then here it is written store. So what is the meaning of this store? It means now take this value from operand stack to local variable stack. After that the operand stack become empty. I have already explained, when we have no item in the stack, it is an empty stack. Then again I will push 30. This 30 will be pushed into the operand stack. Then stack pointer will be incremented by 1. Then we will go to the second portion. Again we will store this 30 into the local variable stack. Then again program counter will be incremented by 1. Then the next term is loading. Loading means again load the item from local variable stack to operand stack. Then again 30 is loaded, and then we will perform the addition operation, which is known as add operation. How add operation is performed? First, these items are popped from the operand stack, and then stack pointer is decremented to its initial position, and afterwards addition is performed, and then again the added value is pushed into the stack. This is how this stack will work, and this will be the final output for this code. Isn't it beautiful? So runtime data area is done. Now we will move to the next part, that is your execution engine. The JVM Execution Engine is the third main component in JVM engine. This is the actual engine that converts bytecode to the machine code and executes the instructions. This execution engine is comprises of all these components. First, what is the use of interpreter? Interpreter reads the class file or the bytecode and executes it one by one. Now here there is a problem. So whenever interpreter reads a particular file, if there exists any repeated calling procedure, that is When a method is called multiple times, it interprets those lines again and again. This is the main problem with the interpreter. And this problem is solved by JIT compiler. JIT compilers solve this problem by using a special component which is known as profiler. Profiler will find the hotspot where the repeated function calling appears. And then the repeatedly executed codes are converted to native code by the profiler so that it can avoid repeated method calls. So it is very important. The interpreter is responsible for executing the specific bytecode, and interpreter suffers from a problem of looping again and again where repeated method callings exist. JIT compiler using a specific component known as profiler solves this problem. It employs or it searches for the hotspot where the repeated method calling appears. And it is the responsibility of the profiler to convert this repeated method calling into a native method call so that this repeated occurrence can be avoided. And the most important component is, I will explain about garbage collector later on also. But remember one thing, this garbage collector is a member of the third component of JVM. This garbage collector has the responsibility of collecting the object or destroying the object which is no longer used. So this is all about Java Virtual Machine.